Welcome to the video lecture series of solid-state devices. Course code is EC301. This is metal oxide semiconductor field effect transistor. Myself, Dr. Shunipa Roy, Assistant Professor of Electronics and Communication Engineering Department, Guru Nanak Institute of Technology. This lecture dedicated for Module 4 field effect transistor. The submodule is metal oxide semiconductor field effect transistor. This is lecture number 13. So metal oxide semiconductor field effect transistor, this consists of type of MOSFET, structure of MOSFET, MOS structure under external bias condition, accumulation, depletion, inversion, threshold voltage, flat band voltage, and all this. This is the lesson plan, structure of D-MOSFET, and also MOS capacitor is there. So the basic construction of MOSFET, this is N channel, this is P channel. So in JFET, this SiO2 layer was not there, but in N channel and P channel FET, one SiO2 layer is there between gate and the channel, between the gate terminal and the channel. That's why the name metal oxide semiconductor field effect transistor. The field effect transistor is the basic phenomena is same as junction field effect transistor. So moving to the next slide, this is the symbol of enhancement mode MOSFET and depletion mode MOSFET. So these lines are broken to indicate that there is no channel present between the source and drain at zero bias condition or while at the time of fabrication. But here for depletion type MOSFET, this line is continuous, indicates that there is a channel at the time of fabrication or under zero bias condition, and the channel is continuous. Current can flow between drain and source terminal. This is the MOSFET basic structure. This is N channel MOSFET. Drain and source are heavily doped and the substrate P is moderately doped. N channel region between source and drain is there. This is channel region showing current flow. As it is N channel, therefore current flows due to the negatively charged electrons. For positive gate voltage, depletion region is populated by the bound negative charges. Similarly, for P channel MOSFET, drain and source are heavily doped, P plus region, and P and the bulk substrate is of N type. P channel region between source and drain. Apply the negative gate voltage, electron pushed downwards. Depletion region populated by the bound positive charges. This is the depletion region inside the channel. The flow of current is positively charged holes. Now, the most important thing is MOS capacitor. So MOS capacitor is an equilibrium device, that is when the external voltage is not applied to the device, the Fermi level of metal and semiconductor are at the same level when no external bias is applied. But when external bias is applied, it behaves according to the voltage applied with respect to flat band voltage and threshold voltage. Flat band voltage is defined as a work function difference between the gate metal and semiconductor when no charge is present in oxide semiconductor interface. Threshold voltage is defined as the minimum gate to source voltage required to induce or create a conducting channel. So flat band voltage, we will discuss it later in detail, but here we will discuss the threshold voltage, that is minimum gate to source voltage required to induce or create a conducting channel. We will discuss. This can be divided into three types. So the MOS capacitor, the heart of the MOSFET is a MOS capacitor. The metal may be aluminium or some other type of metal, although in many cases it is actually a high conductivity polycrystalline silicon that has been deposited on the oxide layer. So this is semiconductor, this is gate metal, and this is the oxide layer. That's why the metal oxide semiconductor name suggested. So when negative external voltage applied, so this side is positive means this side is negative, and it behaves like a parallel plate capacitor. The gate metal is one plate of a capacitor, and the semiconductor, bulk semiconductor, is another plate of capacitor, and the in between oxide layer behaves as a dry electric. So it looks like a parallel plate capacitor. So if this side is negative, the induced charge at the bulk semiconductor is positive. So this is the accumulation layer. E equals to V by D, we know. D is the distance. The majority carrier holes would experience a force towards the oxide. An accumulation layer of holes at the oxide semiconductor junction corresponds to the positive charge on the bottom plate of the MOS capacitor. As per this diagram, as we have applied negative gate voltage. But if the gate voltage is positive, then this side would be positive and the induced charges will be negative. Here we can see the different phenomena. As positive voltage is applied at the gate terminal, the accumulation layer that consists of electrons, whereas previously the accumulation layer consists of holes. This is for N-type, but for P-type, if negative voltage is applied at the gate terminal, then positive charges are induced at the oxide semiconductor interface. So for P-type bulk semiconductor, the accumulation layer consists of holes. The working of MOSFET typically depends on MOS capacitor. MOS capacitor is the main part of the MOSFET. If negative voltage applied, then positive charges will be induced. If positive voltage is applied, negative charges will be induced. So what is happening actually in the energy band diagram of MOSFET? This is particularly applicable for enhancement type MOSFET. As for enhancement type MOSFET, there is no channel is present at the time of fabrication or under zero bias condition. In that case, first thing is accumulation layer. In this case, applied voltage Vg is less than the flat band voltage. Voltage applied to gate is negative. When voltage is applied, MOSFET no longer remain in equilibrium condition. The Fermi level of metal changes by charge of electron multiplied by the applied voltage. Voltage applied is negative, and hence rise in Fermi level of metal takes place while Fermi level of semiconductor remain constant. Voltage applied to the gate is negative, hence negative charge develops near metal oxide junction. Thus positively charged hole travel towards the oxide junction, thus creating positive charge near the oxide semiconductor interface. And due to the accumulation of positive charge, surface voltage is developed near oxide semiconductor junction. Due to this, energy band bending takes place and the value is larger. Value is charge of electron multiplied by surface voltage. Energy band bending is changes in energy offset level of semiconductor's band structure near junction due to space charge. So here we can see in depletion region, voltage applied to the gate is greater than the flat band voltage and is less than the threshold voltage. This is the metal part, this is oxide, and this is semiconductor. Similarly, for depletion region, in this case, voltage applied to gate is positive, hence is fall in Fermi energy level of metal while rise in Fermi energy level in semiconductor. Since voltage applied to positive and hence positive charge develops near metal oxide junction, thus the electrons travel towards the gate creating negative charge near oxide semiconductor junction. Electrons recombine with holes present near oxide, creating depletion region. And the surface voltage develops in depletion region. An effect of this, we have energy band bending in depletion region. That we can see in this diagram. Accumulation layer, we can see this band bending is there. It comes down. This is goes up. Band bending is there. This is goes up. This is depletion region. The region is depleted of free charge carriers. No current will flow from source to drain, as this is N-type and the channel is of P-type. Majority carriers are holes in the channel, so no current can flow through source to drain, and band goes up. Now, what is an inversion layer? In inversion layer, applied voltage is greater than threshold voltage. The reason it is called inversion layer, as the surface is inverted from P-type to N-type near the junction. Voltage applied is very high, hence Fermi level of metal goes down further. Since voltage applied is positive, to gate, electrons travel towards the gate and accumulates near semiconductor oxide junction, resulting development of surface potential. Due to surface potential, energy band bending takes place. From the diagram, P-type substrate near semiconductor oxide junction has intrinsic energy level below Fermi level, and this part of substrate behave as N-type semiconductor, and part above the Fermi level behave as P-type semiconductor. This happened due to concentration of electrons exceeds concentration of holes near semiconductor oxide junction, and the event is called surface inversion. N-type semiconductor acts as a channel for current, and current can flow through this channel on application of positive drain voltage. So now this is the case, inversion layer, as the substrate is of P-type, because the channel that is induced, that is of N-type. That's why this is called inversion layer. So band goes up as EC conduction band energy move up. More electrons means more energy levels are filled up. So conduction band and the whole band will automatically move up. So what is depletion type MOSFET? So with a negative gate voltage, the negative charges on the gate repel conduction electrons from the channel, leaving positive ions in their place. Thereby the N channel is depleted of some of its electrons, thus decreasing the channel conductivity. The greater the negative gate voltage on the gate, the greater the depletion of N channel electron. So remember that for depletion type MOSFET, there is always exists a diffused channel, while at the time of the channel is diffused at the time of fabrication. So already a channel is there. Now if you apply for this N channel MOSFET, if you apply negative gate voltage, positive charge will induce and the channel region gets depleted of negative free charge carriers. It is becoming normally off state from normally on state. So it is becoming it reaches to normally off state as the channel is depleted of free charge carriers. So in case of enhancement type MOSFET, this type of diffused channel is not there. So two lightly doped N regions are diffused in a lightly doped P-type substrate. Two highly doped N regions are diffused into a lightly doped P-type substrate may have an additional terminal connection called SS. So the two lightly doped N regions represent source and drain, and the heavily doped two highly doped N regions represent source and drain connected by a N channel. The N channel is formed by diffusion between the source and drain. The channel, the type of impurity for the channel is same as source and drain. So the thin layer SiO2 is grown over the entire surface and holes are cut through the SiO2 there to make the source and drain terminal. So a DMOSFET may be biased to operation in two modes, in depletion mode and in enhancement mode. When VGS is 0, the drain is made positive with respect to source. Current can flow between source and drain even with zero gate potential. And MOSFET is said to be operating in enhancement. That means already a channel is there. If you apply zero gate potential or the gate or the potential that support the type of charge carriers already existing in the channel, then the device would act in enhancement mode. In this mode of operation, gate attracts the charge carriers from the P substrate to the N channel, thus reduces the channel resistance, which increases the drain resistance. But when VGS is negative with respect to the substrate, the gate repels some of the negative charge carriers out of the channel, N channel, and attracts hole from P-type substrate. Thus, this initiates recombination of hole and electrons. This creates a depletion region in the channel and therefore reduces the number of free electrons in the N channel. And the channel region is getting depleted of free charge carriers. When negative voltage is applied, the more positive the gate is made, more number of electrons from P-type substrate comes in the channel and more current flows. It is now become enhancement mode MOSFET. So this is the phenomena. This is the depletion mode. It is acting depletion type MOSFET, acting in depletion mode. So now the drain characteristics we know. X-axis is VGS, gate to source voltage. Y-axis is drain current. Same device can act in depletion mode as well as enhancement mode. When the VGS is negative, then the device acts as depletion mode as the induced charge supports the channel charge carriers present in the channel. Then it acts as enhancement mode when the induced charge does not support the charge carriers present in the channel, that is opposite charge polarity is induced in the channel region, then the device behaves as depletion mode. But when same polarity charge carriers used in the channel, then the device acts as enhancement mode. So the depletion type MOSFET can act in enhancement mode and can also act as depletion mode MOSFET depending on the gate to source voltage applied. So this is the transfer characteristics similar to JFET and enhancement type MOSFET. This depletion mode MOSFET actually follow the Shockley's equation just like JFET. When VGS equals to 0, ID equals to IDSS. This point, when VGS less than 0, ID is less than IDSS. This point, and when VGS greater than 0, ID is greater than IDSS. See, when VGS is greater than 0, ID is greater than IDSS. This mode actually enhancement mode operation, and this mode actually the left side represent the depletion mode operation and the right side represent the enhancement mode operation in the transfer characteristics curve. Similarly, as we have learned the N-channel depletion type MOSFET, similarly there is also a P-channel depletion type MOSFET. This is the heavily doped P regions. This is N-type bulk semiconductor. P-channel region is already there between source and drain at the time of fabrication under zero bias condition. And if we apply positive gate voltage, then negative charges will be induced. This negative charge will recombine each of the hole present in the channel region, and as a whole, the whole channel region getting depleted of free charge carriers. Then this device acts as depletion mode. But when we apply the negative voltage here, positive charge will be induced here as the principle of parallel plate capacitor. Then, as already P channel exists, but again due to the negative gate voltage, positive charges are induced, so it is enhancing the current flow. Then the device acts as a enhancement mode MOSFET. This is the drain characteristics and the transfer characteristics curve of P channel depletion mode MOSFET and enhancement mode MOSFET, as already elaborated earlier. These are the references. These are the data sheet. While choosing a device, these parameters we have to take into consideration. This is called data sheet. This is particularly for this type of MOSFET. This is the reading material. If there is any question, feel free to ask me this email ID. Thank you.